In this video, I'll be talking about how to design a spiral cam using SolidWorks. Here we have a depiction of some cams. In general, a cam is used to turn continuous rotational motion into either a linear translation or a partial rotation on what is called a rocker. A cam can be an arbitrary shape and rotates and presses against what's called the cam follower, which can take a variety of forms. Typically, a roller follower is going to be the best because it reduces friction and surface wear. However, other follower contact types may be used to reduce cost or complexity. This video will focus specifically on spiral cams, which are good for quick return systems in general. One application of this is launching mechanisms, one of which is demonstrated here. So you can see that as the cam rotates, the outer edge of the spiral presses against a roller follower until it reaches the maximum diameter of the spiral, at which case it is released and the tension in the rubber bands pulls the slider forwards. We used the same principle in our 2014 bot Legacy and FRC. This is our spiral cam we designed for that. This cam drove a catapult and charged springs to a maximum tension of over 550 pounds in order to launch a large ball up to about 28 feet under the maximum shot power settings. I'll create a new part, standard stuff, create a new sketch on the front plane, and now we're going to want to draw a spiral to create the cam from, and you can't really create a spiral from most of the tools you'd typically be using. So what we'll be doing here is going to what's called the spline tool, which is this squiggly, and clicking the drop down to get to what is called an equation driven curve. Now this gives us a couple of options for equation so that we can use to drive the curve, and one is explicit, in which you create a function of y given a function given a function of x, and you set limits on your x values. Now we have to think about whether we can create a function of the variable x such that we can create a spiral profile that looks something like this. And the answer to that is going to be no, because per its definition, a function can only have one output given the set of inputs. And we can see that here we're going to have two y values for the same x, and that holds for pretty much everywhere on the cam except for where y is equal to 0. So we're going to have to figure out a different way to do this. And the way we're going to do that is create what's called a parametric function. In a parametric function, we actually have two different equations. One equation gives us the x values, and one equation gives us the corresponding y values. These are going to be functions of the variable t, as SolidWorks likes to call it, and is typical in mathematics. So your t is going to vary from some value t1 to t2. At each of these points, you're going to have two different equations, and one of these equations is going to calculate the x value at a given t, and one of the equations is going to calculate a y value for that same t, and then you plot all of those points to give you the output curve, and sometimes coming up with parameterization to find x and y in terms of t can be kind of tricky. I'm going to go over a simple example here, which is the example of the unit circle, which is a circle of radius 1. So if we look at a circle, or something resembling a circle, we can see that this does not pass the function test, so we can't write it in the explicit form. So we'll see if we can write this parametrically. The function test being, of course, it has two outputs for each input x. See, there are two y's here, etc., etc. So now we're going to want to find some value y, or some function that will give us x given another variable t, and some function that gives us y given a variable t. Now, the t doesn't necessarily have a whole lot of meaning given your graph in particular, but in this case, and a lot of times it's actually time, which is not on the graph, and that's where the t comes from. But in this case, I'd like you to think of the t of what we're doing is consider, instead of going from left to right on the graph and plotting y values corresponding with your x, think about going around the circle and then corresponding x values and y values that give you each point on the circle. So we're going to have, for each point on the circle, we're going to have some angle, which we'll call theta. And so now we just have to come up with x values and y values that correspond to this third variable theta, so that we can represent this circle. So this is quite easy given trigonometry, we know that given an angle theta then and radius r, that the x-coordinate of this point is going to be r cosine of theta, and the y-coordinate is going to be r sine of theta. Now, since we're representing a circle of radius 1, this will simplify to cosine theta and sine theta. And I'm going to switch theta to t, since that's what we'll be using in SolidWorks. Since SolidWorks asks for the limits on t, we're going to have to figure that out, and that's of course going to be a full revolution, which is 360 degrees, or in our case, we're going to be using radians. So t1 is going to be 0, where t1 is the start, of course, and t2 is going to be 2 pi, because there are 2 pi radians in a circle, of course. So now we're going to go back to SolidWorks and make sure this actually works. So x is going to be cosine of t, and y is going to be sine of t. Enter those equations in SolidWorks, and we end up with something that's very close to a circle. Well, this is just, the only reason this is less than a circle is because I approximated pi. If I tell SolidWorks to use the exact value of pi, it gives me a geometry error because the curve intersects itself, and SolidWorks doesn't like that. So now let's try to do this for a spiral instead of just a circle. Good. Close enough. So the particular spiral that we'll be using is what's called an Archimedes spiral, which I've selected because it's rather simple to model mathematically. In an Archimedes spiral, the instantaneous radius of the spiral is directly proportional to the angle. So looks something like this, where you start at 0 and your radius is constantly increasing until you reach the end of your spiral. Mathematically, in polar coordinates, it can be written as r is equal to a theta, where a is your constant of proportionality. So if you have a large A, it's going to spiral out very quickly, and if you have a small a, it's going to be a very tight spiral and have to make more revolutions before it reaches the same distance. Now, what we're going to want to do is ask ourselves how to determine this A parameter for the spiral we want to draw. In order to do this, you're going to want to determine what your starting and ending radii are going to be. Our minimum radius is going to be determined by how large of a shaft or hub you need to attach to the cam, and then the maximum radius is going to be determined by the travel you need for the cam follower. And personally, I would recommend you have the distance between the minimum and maximum radius be greater, a little bit greater than the actual travel required from your follower, because that way you can put in a mechanical stop somewhere else on the system, so that when your follower comes in, it doesn't slam directly into the cam. Though this is most important when the cam is heavily loaded. If it's not heavily loaded, it's not as big of a deal generally, but if you're subjected this to a high load, or it's going to be moving really fast, it could be really hard on roller followers and the surface of the cam if it just slams into there and stops. So anyways, you determine your starting radius and stopping radius. So given your R1 and your R2, you can say that R1 is equal to A times theta 1, and R2 is equal to A times theta 2, where theta 1 and theta 2 are the beginning and ending angles. Because you're not necessarily going to want to start at theta equals 0, because at theta equals 0, the radius of the cam is equal to 0, and you can't put any kind of shaft through a 0 radius, so that creates a problem for you. So you're going to start at perhaps over here. You have some non-zero radius, and then work your way out, and then you're going to actually end up stopping 2 pi radians away from that, which would be over here somewhere. So now that we have these equations, we can go ahead and do that theta 2 minus theta 1 is equal to 2 pi, because we're generally going to want the spiral to be a complete circle. If you want a part of a if you want a graph something other than a spiral cam, or use only a partial spiral section in your cam profile, you can substitute angles other than 2 pi in this equation. But here we're going to be designing cams that cover a full where the spiral covers the full revolution. So then we're going to subtract this equation from this equation. That's going to give us R2 minus R1 is equal to A multiplied by theta 2 minus theta sub 1. And then substituting in this equation here, we can write that R2 minus R1 is equal to 2 pi times A. And then doing just a little bit of algebraic manipulation, we can say that A is equal to R2 minus R1 divided by 2 pi. So that gives us our constant of proportionality, and given our starting and ending radii. And so then, in order to have limits on now we have these limits here for where to start and stop graphing, we're going to need to calculate our theta sub 1 and theta sub 2. So if we go and since we've calculated A using this, we can go back to these equations here and write theta sub 1 is equal to r1 over a, and theta sub 2 is equal to r2 over a. So now we've calculated this, and we've calculated that. So now what we're going to have to do is convert this equation into a parametric representation, because this is a very nice simple equation in polar coordinates, but SolidWorks doesn't support polar coordinates, so we're going to have to go ahead and convert that to parametric form. So we're looking at r, the radius, as a function of the angle theta. So then if we consider again some trigonometry, say that the angle, we have our angle theta and r, so then we can once again represent any point on the spiral using r and theta like this, and to get the coordinates we simply use the fact that x is equal to r cosine of theta and y is equal to r sine of theta. And so we can't have r in our parametric representation. Everything has to be a function of only theta, so we can go back to here and say that r is equal to a theta. So then we're going to end up with x is equal to a theta cosine of theta, and y is equal to a theta sine of theta. And then just to match the SolidWorks notation, you can say x is equal to at cosine of t, and y is equal to at sine of t. So that's all we need to do mathematically. So then what I did and what I recommend you doing, as well as what I recommend you to do for any calculations you need for your designs, is put this into SolidWorks. Not SolidWorks, into Excel. So what we did up here is we took as our inputs your minimum and maximum radii, and we found functions for your constant proportionality A and your starting and ending angles. So I made an Excel spreadsheet that will calculate those. These are just implementations of those equations in Excel. So you can go ahead and enter any arbitrary radii here and get these values to plug into SolidWorks to generate the cam profile. So let's say we have R1 is equal to 1 and R2 is equal to 3. So then we can take these numbers, this A, and plug it in for the value of A in our parametric representation here, and we can take the thetas to plug in as our starting and ending points. So we'll go ahead and go to SolidWorks and we'll copy this and say x is equal to a times t times cosine of t, and y is equal to a times t times sine of t, and then we'll copy over this value and this value for our starting and ending parameters. And now we have a spiral, and just have to fill in this gap here to create a spiral cam profile. And so what we want to do at this step is to check our work a bit, because you always want to check your work to make sure you did everything correctly, of course. So going to measure, the easiest way to do this is to just measure the starting and ending radii and see if they're what you wanted. So we have a minimum radius of 1 inch, and we have a maximum radius of 3 inches, which, as you can see, is exactly what we asked for. So this cam profile appears to be what we want. So then, now that we have this profile, we can simply extrude this to whatever thickness is required. And we can't mill a sharp corner like this, so we're going to want to put a bit of a radius here. You're going to want to make sure that your radius doesn't interfere with any sort of cam follower that you may need or that you will be using. So then we have that, and then you can just create one last sketch, or then put a a point here, exit your sketch, then use the hole wizard to just use your hole wizard to locate a hole to put your drive shaft on, and add whatever other features you may find necessary. So I think that about wraps it up in terms of the design of the cam, how to model a cam and the mathematics behind that. I intend to create an additional video at a later time that will explain a simple method for determining the torque requirements to actually drive this cam, so that you can drive, choose the appropriate drive gearing and all that. So thanks for watching, and I hope that this was informative. Bye.